First of all, thank you, all of you, for coming to this talk. And also, thanks for the mobilization organization for allowing me to speak for another year here. For those who don't know me, my name is Saul Diaz. I'm an Android developer. I've been a developer for maybe 12, 13 years, and I've been doing Android for 8 or 9, I think. And I'm a functional programming apprentice, and I love object-oriented programming. So let's talk a little about object-oriented programming first, because I suppose that most of you are more familiar with this paradigm rather than functional programming. Okay. Back in the 50s, the way developers used to code was using machine assembly. The problem was that this code was not much portable because it was made precisely for the machine, for the architecture it ran on. And also the code was not very maintainable because it was not really readable. And probably just the people who made that program and some wizards of machine assembly would be able to modify the program. So the people there thought that there might be a better way, a better solution to write programs that could run in many machines and were more easily maintainable and understandable. And that's how procedural programming came to happen. In 1956, Fortran, which was the first commercially successful program, came to happen. And in 1959, COBOL, which is still used in a large database of many banks, started to be used. This used a more high-level approach, procedural, imperative, with blocks separating data from the manipulation of that data. And this is how, more or less, the modern history of languages happened. But take into account that in old times, most of the developers had a mathematics or physics background. And they believed that maybe building a paradigm where mathematics, with all its correctness, with all the robustness they have, could be a way to even improve the programming style. And in 1958, arguably, Lisp, and I want you to reflect a little on the years we are talking, because Lisp in 1958, more than 50 years from now, set the basics for functional programming. And it was good, it was more or less maintainable, but then more and more developers were becoming mainstream, and not all of them were starting to come from a mathematical background. And this is how in 1967, I think, with Simula 1, and in 1972, with Smalltalk, the basics of the object-oriented programming you use now started to appear. And object-oriented programming was born in the notion that maybe if we build the code on the same intuitive way, with the same representations we have in the modern world, that could be helpful to understand the code, to separate the code, and to make it more maintainable. Sorry, there you go. This was the notion of object-oriented programming. And this led in 2018 to code which is readable like that, because as in a friend Paco works, one of Arrow's maintainers, moot point about functional programming is that this code is readable, but functional programming code is not so much. Or is it? He likes to say, and I think he's right, that it's not that this code is readable and functional programming isn't. It's that we are familiar with object-oriented programming, but functional programming, we are not so familiar as you are familiar with Polish, but I cannot read Polish. Not because Polish is not readable. It's because I don't know Polish. So maybe if we can learn a little more about functional programming can become also readable. But let me, before starting, let me into a little secret. 100% of bugs are caused by source code. And that's an axiom, that's a fact. Okay? And functional programming sometimes helps us to build more concise and to-the-point code. And this code, which is work coded in a functional way with just the plain Kotlin STD. This doesn't have arrow. This doesn't have any weird framework. This is pure Kotlin. And pure Kotlin allows you to make the previous snippet I showed you in half the lines of code. And this means half the chances of making a bug, making a very robust code. And that's one of the reasons we should also look far away from our noses and far away from only object-oriented programming. Because as professional developers, the more tools you know, the better developers you are. Because you have more tools to approach problems that you were solving maybe in an erroneous way, or maybe you didn't know that they will have a solution. And it is said that when the only thing you have in the hand is a hammer, everything looks like a nail. If you only have object-oriented programming in your repertoire, the only solutions you are going to be able to provide are object-oriented ones. And imagine another tools you take for granted today, like unit testing, integration testing, continuous integration, solid principles, or I don't know, whatever you may think of. If you didn't know them, you would be a worse programmer, because you would, in the end of the day, write worse code, less testable, with a less separation of responsibility. And we are aiming to become great programmers. I assume all of you who are here today in mobilization are assuming to become better programmers. And the only way you can do it is through learning new things. Like, in this case, today we are going to learn about what functional programming can offer to us. And functional programming, besides all the mathematics which is behind, which we are not going to talk about today. This is a talk for people who are more used to object-oriented programming. You don't have to know how to build a car in order to use the car. So today we are going to learn how to use functional programming. And if you want to delve deeper into the mathematical principles that governs it, you are more than welcome. But maybe later. And like I said, functional programming has some principles that we should be adopting them right now in our object-oriented programming. The first one is mutability, or immutability. Okay? I want to make a little separation here, because constant does not necessarily mean immutable. Like you see in this really like stupid snippet of code, a shallow copy of this mutable list is constant. I cannot change the list it is pointing to. But if I make a mistake here and I clear shallow, I am cleaning also origin. And our origin list we just had a bug in our code, which is going to take us time and money to fix it, because we need to debug and we need to understand what's going on. But if we make our data models immutable, no matter what we do here, because we are not going to introduce bugs, and immutable data models have a few improvements, like you are removing the state out of your program, and therefore your code and your data models in this case will be more resilient to concurrent multi-threading environments. It is true that if you go copying and modifying all these data models along your computations, you are going to use up more memory. This is a valid moot point. But if you don't leak them, the garbage collector will eventually take care of it. So it is not so important, especially on the mobile level, when we don't use like huge amounts of data. The second principle I want to talk about is purity. And purity, in the terms of functional programmers, is separating side effects from the things that doesn't have side effects. This means that if you have a function, every time you feed it the same input, you're going to get the same output. And this means you are not going to perform any side effects, which is like writing to a database, querying an API. So in that case, it's like building a big unit testing system. You are going to be pushing the side effects to the end of your computation, and you are going to have a big part of your code base, which is going to be also, like I said in the previous principle, it's going to be stateless, and therefore its testability is going to be greater because you are going to be able to fulfill one of the first principles of unit testing, which is the test will be able to be repeatable, and you won't need to be clearing a state out of your tests after, because there's no state to begin with. Well, this will be like how this will evolve. Okay, so every time I increment purely my code, it's going to be able to do. And finally, higher order. Higher order is a prerequisite of functional programming languages, which is that you are going to be able to to use functions that can receive other functions or can output functions at themselves. And this is going to help you to produce, for instance, a higher level of polymorphism, because a function is defined by its inputs and their outputs. And therefore, you can change on runtime different implementations of the functions you pass to other functions to build, like I said, maybe a polymorphism of functions, or even you could build in Kotlin a factory of functions if you wanted to. And this gives us to approach several problems, classic object-oriented programming, especially in languages like Java 6 or Java 7, which doesn't allow to higher order, to simplify a lot the code you want to do. But it's OK. Enough talking of theories. We are going to make a small example of how do we work with functional programming. OK, we are going to make a small code in the presenter of this application, which is this screen is just the registration form for any app. OK, we are going to do 4 steps. First, we are going to retrieve the input data from the view. Second, we are going to validate that input data to ensure that maybe there's a username put there, the password is strong enough. Finally, we are going to believe that we have a pure API REST, okay, and we are going to post a user to the backend, okay, and we are going to perform a login afterwards. And with every good presenter, this is the bread and butter of coding, we are going to notify an error if something happens, or we are going to be able to get into our app. So the first thing we want to do when retrieving the data is actually checking that the data is even there to begin with. And this is done through a data type. Okay, a data type in functional programming and in Arrow. Okay, it's an encapsulation of a certain coding pattern. Okay, so in this case, option represents nullability because in functional programming we are working all the time with functions. We are forced to be returning things on our way back. And usually, handing nulls in functional programming is not very common, and it's not very advised. Okay, this data type option is it's implemented with a select class, which is sum, and none. None takes no value because there's nothing. We are modeling absence. Okay, and we have several idiomatic ways to lift. Lift is a term in functional programming which means bringing a data type. Bringing a type into a data type. Okay. I will explain. Well, this will be more or less how you would naively code option with a very silly object-oriented programming way, so you can understand more or less what's the meaning of option. Okay, it's like we will be writing a decorator for a nullable object. Obviously, this part is also solved by the Kotlin language itself. So this part of in this naive implementation doesn't make much sense. But I'm going to show you how to manipulate and work with data types. Okay. So imagine, let's make the experiment of the Schrodinger's cat. Okay. So we have a cat. Our cat name is Schrodinger. Okay. And we wrap it into an option data type. Okay. In this moment, we stop having a cat, and we just have an option of a cat. And whatever is in the box, okay, imagine this as a box, is totally irrelevant. We could have a cat or not. But because of the declarative, nature of functional programming, we are going to be able to speculatively operate over that probable value inside of it. Okay. In this case, we use the map function. Okay, which the only thing that it does, you will be probably you will be used to this function because it's already on the collections std for Kotlin. Okay, and the only thing it does is you will map the probable cat inside of our box to the string representation of the cat. So we will stop having an option of the cat to have an option over a string. And we still don't know if there was a cat to begin with, so we don't know if we have a string there. Okay? And this code will only execute if there was a cat inside of the box. If there wasn't a cat inside of the box, this code will do nothing. And eventually, you will want to see what's inside of the box, okay? And for that, we have the fold function. Again, you are familiar with a flavor of the fold function in the Kotlin standard library, okay? And when we open the box, we will be forced to handle both of the cases because in the end, we are working with the option as a function, and we will have to take care declaratively what happens if we have a cat, or we had a cat at the beginning, or not. In this case, if we don't have a cat, we just output a default value, and this is a very basic implementation of a null value, okay, of the new null value pattern. Or if we had a cat to begin with, we mapped our cat into their string representation, so we return it. And the name of our cat was Schrodinger, so we will have here Schrodinger. If you notice, there is like two values you can take for a data type and for most data type and type classes of Kotlin, of Arrow and functional programming, and the result case, okay, the success case goes always off the right, and the error case goes always at the left. So that's why you will hear that data types or type classes are right biased. This means that you will only apply a computation over the data type if it's the success case. If it's the error, you will not apply that computation. Okay, and this is how we will extract the text from our view. You know that sometimes you can run into problems with Android, and maybe you get triggered in a weird life cycle where your view is not initialized, or maybe you are in one of those strange Chinese phones which have a strange Android implementation, and maybe the edit text is there, but the text of the edit text is not there. So with this code, we will ensure that we are protected from nulls from the life cycle. We are protected from nulls from the from the errors from the framework. And finally, we'll be able to get the data, okay, in this case our username, or an empty string if something went wrong, because we would be mapping a hypothetical edit text to its editable representation and the editable representation to the string. And these two lines will not have any effect if there was no if one of these steps went wrong to begin with. So we will do the same for password, and we're ready to go. Now we are able to write text on our on our edit text, and we are sure that we are getting a response, and we are not going to have to handle any kind of weird situations or nulls or whatever. So now we want to validate the inputs. For validating the inputs, what we are going to use is the valid data type. As you notice, the API is kind of similar with option. It's because in functional programming and Arrow, what you aim is for having the same API for all the data types. So once you know the API for one, you can apply that knowledge to all of the data types and all of the type classes every time. Okay. In this case, validated. It's implemented by a select class. Okay, valid and invalid, and with and as with option, you have idiomatic ways to lift a type into a valid type. Okay. If you notice that valid now takes two types. Okay, a success type, which could be a response, or an invalid type, which could be a string or whatever you want. Okay. The good thing about validated is that it allows to accumulate errors. So you use a slightly concrete implementation of valid, which allows you to return a non-empty list with errors in the left side. So you can accumulate several errors, and you can guarantee that this list is never going to be empty, because the implementation does not allow for having two values at the same time. You can only have a success case or an error case, but not both. Okay. But before continuing, let's make a detour for a minute, and let's talk about how you handle errors in functional programming and Arrow. Okay. You have several flavors depending on each case you want to face. You have try, which is the equivalent of a try-catch block, okay, but it doesn't break the flow of the code, which is very important in functional programming. Then you have validated null, which allows you to take two type of results, and then you have either, which you will have seen the usage in almost talk if you were in the talk earlier with TDD in Kotlin. Okay, but let's compare them face to face. I'm adding an option here because one of the gurus of functional programming told me that he considered it to be a way of handling errors. Okay, so in option you can give any type for the result. You get nothing in the error case, and you model the error as the absence of that type. Okay, try. You can take it any value for the success case, but you can only return throwables. You can only return exceptions. So it's only used when an exception can give you enough feedback to continue with the implementation and know what was wrong. And then validated and either allows you to have any type for success and error cases. And the difference, more or less, is that you can accumulate errors with the non-empty list flavor, and either is when you only need to return one single error. Okay, usually the result of a computation that can have a success or error case. So what we are going to do and what we intend to do, I want to validate the whole form in a single pass, okay, and know if all the fields in my form are valid or not. We are going to perform a number of validations here. We are going to see if we actually have anything inside both of the edit text. Okay, we are going to check, for instance, that the password is long enough. If the password has like special characters that make it with enough strength. And we are going to do this with a functional programming pattern called applicative. Applicative is the functional programming pattern that allows independent computation. Note that I'm saying independent and not parallel, because in this case, we are going to run all of this in the same thread. Okay, but with certain things that we will see later, you maybe even do parallel computations and output a result in the same way. And it's done with this simple and easy code. Let me read it for you. Okay, we are using an instance of applicative. Okay, for the validated data type. Most of the data types will have their own validated options, so you can check if it's valid, or maybe you could check with option if you have a lot of data in the same fashion, okay? And we are passing it through the semi-group implementation, which semi-group is a type class, okay? I mentioned type class before. Type class, you can see it as an interface, as a trait of an element, which instead of being implemented inside that type, okay, it goes outside. And the only the trait that semi-group provides is combination. So we are going to combine all these 5 checks, which could be up to 20. I think the library has defined up to 22. We are going to combine all these 5 checks invalidated, and we are going to use it through the applicative pattern. Okay, and this fix is to build like the box, the big box, which is compressed of these 5 checks. This would be like the continuation of the code. Okay, we would start here. Okay. All the validated applicative error would be here. And now, as you've seen before, we are going to fold. We are going to open that box. We are going to see what's in this box, okay? And we can have a result, or we can have a list of errors. We use a select class to give all the options the error can take, okay? And what we are going to do is going to iterate over all those errors we received in a single pass, and we are going to feed them to the UI. So in this way, instead of having a bad user experience for the user, like clicking register, the password is not strong enough, is not long enough, correcting it, clicking again register, and saying that the password requires a capitalized letter or a special sign, so it's strong. We have managed to do it just in 5 or 6. All the logic is in 5 or 6 lines, and we could scale it to whatever kind of checks we want to do, and we would receive all the data, all the results, in a success case or an error case. Okay. But now it's time. Now we retrieve the username and the password. We validated the username and the password, and now we want to do background work. Is it hard to do background work in functional programming? Not really. We use a type class called IO. Okay, IO is like the most generic type class for side effects. So this means that when you are going to use IO, you are going to perform something which is not going to be repeatable. Okay. In this case, we are using this lambda to call our API in a background thread. Okay, because the IO and the async type classes are used for side effects and background work. And as you saw, we are going to return automatically an either. By default, is a throwable, and a string representation of whatever. Okay, and we are going to use this result, and we are going to fold it to extract again from the box. You see a pattern here, fold, and so we are going to know if we receive an error, and therefore we will notify our view, or we receive a success, and we notify a success, or we do what we have to do. But maybe I/O is not for your tastes, because all the people here, I suppose that they like Kotlin. So maybe let's use coroutines. Arrow has integration for coroutines. Instead of using I/O, we are going to use deferred K. Okay? And the coroutines integration in Arrow guarantees that if the coroutines can do it, you can do the same with deferred K. What we are going to do is we are going to launch a coroutine in the common pool in the background, and the result will come on the same fashion, or as an error, or as a success. You see that the API doesn't change at all, even if we are using a different framework to backup or background work. But let's get it a little even longer, okay? Let's introduce another functional programming pattern, which is called the Monad, okay? The Monad, it obviously has a very popular mathematical definition, but what you have to know about the Monad is that is the pattern for sequential execution. Okay, this means that when you are using Monad, what you are going to use is a chain of calls, okay, or a chain of functions, and the output of the first function is going to be the input of the next, and the output of the second function is going to be the input of the third. In this case, it's even a simpler example because we are using a pure REST API. The only thing we want to know is that this line here doesn't throw an IO exception, and that this line here doesn't throw an IO exception. And with this code here, what you can guarantee is that in order to receive a result, you need these two lines of code, these two ethers here, not to return an error case. And if you any of them return an error case, we are going to require to notify the error with the exception in this case. And we will take the measures required and the error text necessary for the user to know what's going on. Basically, what we are using here, it's a deferred for the coroutine implementations. But we are going to use the extensions Arrow provides to bind these two computations into one. Okay, remember, two boxes. In this case, it will be two boxes which are deferred, okay, into one big deferred that we are going to execute in background. Because we are using here common pool, we cannot guarantee that the result is going to come in any particular thread. Okay, so we will force a third coroutine that returns our result into the UI thread. Okay, so we don't run into any exceptions with Android. Okay. A more advanced error handling compared with Monad and Applicative is that with Monad you have a fail-fast strategy for handling your error with multiple computations. Okay, and Applicative is more like it's more accumulative, so you can run a number of things independently, pseudo parallel, so to speak, and you can receive the error once all of them passes or not. Okay, and this would be more or less the functional programming result, which is great. It's not a bad code. It's robust. Some parts of it, it quite gives the edge over object-oriented programming. But maybe it's not as, like we said, it's not as readable as we want it to be. So here's where object-oriented programming comes to the rescue, because why do I have to keep with just one paradigm where I can fuse both of them to get the best of both? In this case, we are going to extract our validation strategy into a class with the deferred execution. Okay, remember that in object-oriented programming, if you use your constructors to hold logic, not only you are doing it wrong, but also you won't choose when to perform the logic of that object. With this, we can defer the actual validation when it's more comfortable to us, instead of when you are creating the object itself. We are going to tune it a little here, so when the result comes, which would be a valid of 5 things, we are going to return a tuple. We could return a pair too, but tuple is a tuple of 2. It's something inside Arrow. Okay, this is a personal choice in writing this code. So is the last thing. So we are going, like I said, we are building a independent validation of all these statements. And then once we have it, we are going to map it. Remember what I told you about map? If this is the list of form errors, this line here is not going to execute. So I don't have to worry. I don't have to check with an if, if the result of this execution, if this computation is a success or not. Because this is only going to apply if all of these 5 checks pass. Okay. With defer, we could easily build a naive system for use cases. Okay, and we can use these 2 here. Okay, with register user and login user, and maybe we can abstract away with an extension function the way to return the results to the UI thread, and with a little of abstract methods, we can move all this silly code into the view. And finally, our results of merging functional programming and object-oriented programming, it's here. Registration here, I think I missed this slide, would be abstracting all the deferred extensions, just using the 2 use cases that we defined here. Okay. Because now, thanks to functional programming, we have a robust way of getting our data from our form. With our form validator, we can validate the data with a very simple code inside, and with Monat, okay, we can combine these two use cases that can work perfectly independently, but in the Monat pattern, we can bring them together to perform a more complex computation and return the result precisely here. Okay. We use a lot of techniques in this small code. We use null handling from functional programming. We use independent computation. We use sequential computation. We use success and error result handling. And from object-oriented programming, we benefit from solid principles of extension functions in Kotlin, of deferred execution, and we build a more or less clear architecture. Obviously, the code we wrote can be tweaked a little to be improved. But well, this was like a small example of what we can do. But functional programming and Arrow, in this case, has a lot of more things to offer, which will take me like another 2 hours of explanation because there's a lot of things. But for instance, with the optics module of Arrow, you can build immutable models on a very simple way, okay? Just with the annotation processor and the optics annotation, you can build nested data models like you use in your applications and make them immutable in a way which is much more simpler to modify something and return a copy of it that it is in object-oriented programming. But even more, with higher kinds, which is a particular application of higher order, we can build abstract code that can separate the logic from the actual delivery method. For instance, we use this to build a use case system. But imagine that tomorrow you don't like coroutines and you prefer to use, for instance, RxJava. Okay. You can build higher kinds of your use cases, which not only you input the logic you want to perform, but also the delivery method you want to do with the type class async. So with the same exact logic, you can execute your code in coroutines in a more general async way with RxJava and with React. And all of these frameworks are already supported by Arrow. And you could make a totally abstract computation from the delivery method with the same code, okay? Logic code. I'm wrapping up because I don't want to take any more of your time. Don't, like we said at the beginning, become a better dev by learning more tools, because with those tools, you can apply better solutions to the problems you face every day. And finally, don't be dogmatic. Object-oriented programming is no silver bullet. Functional programming is no silver bullet. And those paradigms have been around for more than 50 years. And the more you know, the more you can make it. Oops, sorry. And remember that maybe this code can become readable. But something that object-oriented programming is that this code is more intuitive than functional programming is. But don't reject any of them. Put them together and get the best from both worlds. Thank you very much.